All right, silly little cartoon. Bless you. All right, so these are our notes on ionic and covalent compounds. So we start off by looking at just some of the chemical families. We talked about the periodic table, so the noble gases. What was the big thing with noble gases? They don't react. They don't like to play with anyone. They don't share because they already have full shells, so they're already happy. Then we had the halogens, so that's group 17. And the halogens are all one short of being full. So they're always trying to find another electron. And we said that if you look at the periodic table, as you move up and to the right towards fluorine, you get more reactive or less reactive? More reactive. More reactive because fluorine's smaller, so fluorine's able to has a smaller shell structure, so is able to pull in electrons because it's the nucleus that holds or pulls in electrons. Then we looked at the alkali metals. This is group 1, so this would be like lithium, sodium, potassium, and we said that they're very reactive. So they're all trying to get rid of one electron. And in this one, it was the opposite. As you move down and to the left towards francium, they become more reactive, and that's because they're bigger. They can't hold on to that single electron as effectively because the outer electron is further away from their nucleus. And then the alkaline earth metals, group 2, so this would be beryllium down. They're reactive but not as reactive. They all have 2 valence electrons, so they're all looking to get rid of 2 electrons. So that brings us to ions, and this is the new part of the notes. So this isn't a group. Ions are any atom that has gained or lost electrons. So as we've seen, atoms will gain or lose electrons to fill up that outer shell. So once they do that, they're now considered an ion. All right? So chlorine, for example, there needs to find an electron, add it to its outer shell, and when it does that, it becomes negatively charged, and it's called an ion. Sodium is the same way. There's sodium. So sodium is looking to give away an electron, doesn't want it anymore. So once it gets rid of that one of those negatively charged particles, one of those electrons, it becomes positively charged. So now it becomes a sodium ion. Okay, so one thing that we need to discuss is the idea of sharing, giving, and taking. Now, on Sesame Street, we're all, Zoe, here's a pen. You're welcome. So, did I just share with Zoe? Sesame Street would say yes. I just shared with Zoe, right? You have a pen now, right? But in the atomic world, that's not sharing. Zoe took my pen. I gave her my pen. In the atomic world, for us to share the pen, we would have to do this. Hold on to the pen. I will also hold on to the pen, and we will write something together. Now we're sharing the pen because we're doing it at the same time. That's sharing. And in atomic world, that's how they share electrons. They're both holding on to the same electron at the same time. If I am giving an electron, I no longer have it. Now Zoe has it. Zoe took that electron. All right? So do you see the difference between how humans would say share? Like in humans, this is sharing, but it's in atomic world, that's not sharing. Okay? So look, we wrote hello very messily. So in this situation here, sodium is not looking to share its electron. It's looking to give it away. Chlorine is not looking to share an electron. It is looking to take one. All right? So they can share in other situations, but their ideal situation is to get rid of it. Okay? So here we have... Oh, sorry, a little more notes. So an ionic compound is formed when 2 ions swap electrons. So this giving and taking of electrons results in an ionic bond because they're attracted to each other. So you've all heard the saying opposites attract, right? Well, again, in the atomic world, this is true. You've got positively charged particles, they're attracted to negatively charged particles. So they will, like magnets, kind of just stick together. All right? And when you get a whole bunch of them doing that, then you get a new compound. So sodium and chlorine, you get positively charged sodium, you get negatively charged chlorine. They are attracted to each other. They form sodium chloride, which is just salt. All right? So we learned, we saw in the Bill Nye video what sodium and chlorine can do on their own. But when they combine together, they form salt. So very good. We've got a model here of sodium and a model of chlorine. They're starting off neutrally charged. So you can see that sodium's got that one, on the left here, that one extra electron on its outer shell. Chlorine's got 7 on its outer shell. So sodium wants to get rid of one, chlorine wants to gain one. So watch what happens. Well, watch what happens if I actually advance the slide. There we go. Zoom. See that again? So now they both have full outer shells and they're both happy. So now we've got an issue with this one. Magnesium is in group 2. So how many valence electrons does magnesium have? 2. And if it wants, does it want to go and find 6 or give away 2? Give away 2. It's all the numbers game, right? So it's got those 2 valence electrons it wants to give away. If it finds some fluorine, which is what we've got on the right there, how many can fluorine take?
1.
Just 1. And once fluorine takes 1, it's done, right? Fluorine's happy. She doesn't want it anymore. So what do we need? Well, we need a couple of fluorines. We need 2 fluorines for this to work. So we need 1 fluorine to take 1 magnesium electron, and the other one to take the other one. So now both fluorines are happy, and magnesium is happy. Because magnesium has a full outer shell, got rid of those 2 valence electrons. Each fluorine took 1, so that's why fluorine both of them are happy. But that's where we get this formula here from. It's MgF2. And that means for every 1 magnesium, we need 2 fluorines. Because 1 fluorine isn't enough, right? So it's all about the ratios. Okay, so we've got some volunteers up here. So Zoe, you're going to be an oxygen atom. All right, so looking at oxygen, how many electrons does oxygen want? 2. So you want 2 electrons. You're not going to be happy until you get 2. Now, Melissa, you're going to be a sodium. No, we've done sodium. You're going to be lithium. Okay, so you're lithium. So how many valence electrons does lithium have?
1.
Just 1. So that's why I gave you the marker. So that's your valence electron. All right. So you're just kind of floating around, and you kind of bump into each other, and you say, "Hey,
Hey.
can I have your electrons?"
Can I have your electron?
All right. So you take all the valence electrons that she has. Okay. So you grab 1.
Happy.
You're not happy. Why aren't you happy?
I want another one.
You want another one.
I'm happy.
Are you happy?
Yeah.
Yeah, you're very happy. So you're happy because you've gotten rid of your valence electron, right?
Yeah.
So you've got a full outer shell. You're good. You're not happy though. What do you need?
Another electron.
You need another electron. Well, we just so happen to have Megan here, who is going to play the part of another lithium atom. So there's another lithium. Well, wow, you could have asked first.
Oh, can I have?
So you're gonna take her valence electron too. All right. So now, Megan, are you happy?
Yeah.
Yeah, because
I got rid of my valence.
you got rid of your valence electron. You have a full outer shell. Zoe, are you happy? Yeah, you got a full outer shell. You got those 2 electrons you were looking for. How many lithiums did it take, though?
2.
It took 2 lithium atoms to make you happy because you have 2 missing electrons. Come over here a little, Megan. Okay, there we go. All right, so... All right, so next class we will continue with the notes and we will look at naming ionic and covalent compounds.